Okay, in this lecture we're going to start our Chapter 3 material on techniques of integration. And in the first section, 3.1, we'll talk about a technique known as integration by parts. So before we start this section and the material in this chapter, I'll mention that throughout Chapter 3 we're going to look at several different techniques of integration. And something that's often a little bit challenging for students is determining when you should use a particular technique of integration. So if I just give you an integral, how do you know which of the techniques you're supposed to use? So that's something that as we're moving through Chapter 3, I'm going to try to stress. Is first off, before we introduce each technique, how do you know that you would use that technique for a particular integral? Now, we've already talked about one technique of integration in our Chapter 1 material, which was integration by substitution. And I mentioned in that section that we would use a substitution if we're trying to integrate a composite function, which can't really be simplified. So for this lecture, before we introduce the idea of integration by parts at all, let me start by stating when we would use this method of integration by parts. So I'll put a little note up here that this technique is used to integrate products of functions which can't be simplified. So let's say just products of functions. Now we've considered some examples already of integrating products where maybe if we're multiplying two polynomials, we could expand and then integrate term by term. So really we're just using integration by parts to integrate products which cannot be simplified any further. Also, we would use this for logarithmic functions. So if we're trying to integrate something involving, say, a natural logarithm and a substitution doesn't work, then we might also make use of this integration by parts technique. Or we could use this technique to integrate inverse trig functions. So we know how to find antiderivatives or integrals of the standard trig functions, say sine x, cosine x, tangent x, secant, cosecant, or cotangent. But what about the inverse trig functions? Like let's say arc sine of x. How do we find an antiderivative of that? And we're going to make use of this method of integration by parts to do that. So now that we've discussed the types of integrals where we would use this method, let's introduce this method of integration, and we'll start with the following theorem. So this theorem is often referred to as the integration by parts formula, which says that the integral of u times dv is given by uv minus the integral of v du. So it's not immediately clear what we mean by this formula or what it represents, but the idea is we're trying to come up with a technique to find an antiderivative of a product of functions. Now we know from Calculus 1, from the product rule for differentiation, that the derivative of a product of two functions is not just the product of the derivatives of those functions. So it also doesn't work for antiderivatives. That is, the antiderivative of a product of functions is not just the product of the antiderivatives of those two functions. So we're trying to come up with a sort of product rule for integration. Now there is no like cut and dry formula like we had for differentiating products, but typically for handling products, we're going to use this integration by parts formula. So to prove this theorem and see how it will allow us to integrate products of some functions, let's consider the following. So I'm going to define a function h of x as the product of two functions. Let's say f of x and g of x. Now, I know by the product rule, for differentiation, the derivative of this function, that is h prime, would be given by f prime of x times g of x plus f of x times g prime of x. Or, for some notational simplicity a bit later in the problem, in this first term, I'm just going to reverse the order of the product of these functions. So let me rewrite this as g of x times f prime of x plus f of x times g prime of x. So I've just reversed the order of the product in those first two terms. It doesn't change its value. Now, if I integrate both sides of this expression, so let me say integrating both sides, let's see what we have. So I would have on the left-hand side the integral of h prime of x. I'm going to integrate with respect to x. And that would be equal to the integral of g of x f prime of x dx plus the integral of f of x g prime of x dx. Now, on this left-hand side of my equation, I'm looking at the integral, or the antiderivative of the derivative of h. So by the fundamental theorem of calculus, the antiderivative of the derivative of a function would just be the function itself, h of x. So I have h of x is the integral of g of x f prime of x dx plus the integral of f of x g prime of x dx. But recall that h of x, this function on my left-hand side, was defined as the product of f and g. So we have f of x times g of x is equal to the integral of g of x times f prime of x dx plus the integral of f of x times g prime of x dx. So if I solve this equation for this integral on the right-hand side, what I have is the following. F of x times g of x minus the integral of g of x times f prime of x dx is equal to the integral of f of x times g prime of x dx. And so if I just make a substitution or a change of variables for this equation, then I get my formula in the theorem. So let's see how this works. If I were to make a change of variables or a substitution for what I'm calling things, as u equals f of x and v as g of x, then if I calculate the differential du, I would have f prime of x dx. And if I calculate the differential of v, I would have g prime of x dx. So looking at our formula that we had in the line above, if I rewrite this in terms of u and v, this says u times v minus the integral of v times du is equal to the integral of u times dv. And this is the formula that was given in our theorem. This is known as the integration by parts formula. So what this theorem allows us to do is take an integral that would be something of the form u times dv, and I could rewrite that integral as u times v minus the integral of v du. And my goal in this method of integration by parts is to choose u and dv in such a way that this integral that I get by applying the integration by parts formula is something easier to evaluate than the integral I started with. So that's the general idea here of integration by parts. We're going to use this formula to try to reduce the integral we're given to an integral which is a little easier to evaluate. And as I mentioned, this is typically going to work out well if we're integrating products of functions which can't be simplified, logarithmic functions, or inverse trig functions. So let's look at some examples to illustrate how this method will work. So in this example, we're asked to evaluate each integral. And in part A, I have the integral of x times e to the 2x dx. So I see here that my integrand is a product, x times e to the 2x, and I can't simplify this at all. So the fact that we have a product of two functions which can't be simplified should make us think of this method of integration by parts. Now, our first step in the method of integration by parts is to choose part of our integrand to be what we call u, and the remainder of our integrand will then be dv. So as a reference, maybe at the top of our page here, let's copy down the integration by parts formula again, which says the integral of u dv is equal to uv minus the integral of v du. And I'll mention this is very useful to have memorized. Over the course of the semester, we'll use this formula so much that I suspect you'll memorize it just naturally as you work through homework problems, but it helps to have this formula memorized early on. So in this example, I'm going to choose u to be the first factor in that product. That is, u is going to be x, which means that dv, so after I choose u, everything else in my integrand is going to be dv. So here, after I choose u as x, that means that dv has to equal e to the 2x dx. Now, once we have these expressions, let's think about what we need for the integration by parts formula. So this is equal to u times v. Now, I already have u, but the question is, well, what is v? I don't know what v is yet. And then we have minus the integral of v times du. Now, I know what u is, but I still have to find du in order to apply this formula. So after we choose u and dv, our next step is to calculate du, that is the differential of u. So if u is equal to x, then its differential would be 1 dx. And to find v, well, if we know the differential of v is e to the 2x dx, then v would be the integral, or the antiderivative of e to the 2x dx, which is 1/2 e to the 2x. So applying our integration by parts formula, the integral of x times e to the 2x dx, which is the integral of u dv, is equal to u times v. So let's start by taking the product of u and v. So multiplying these two terms, we have 1/2 x e to the 2x power. And then we are subtracting the integral of v times du. So here I've got the integral of 1/2 e to the 2x dx. So after we apply this integration by parts formula, I'm left with a new integral, and this new integral is easier to evaluate than the one that we started with. It no longer involves a product of two functions. It's just the antiderivative of e to the 2x, the constant 1/2 I could bring out in front of my integral. So that's the idea of this method, is we're going to try to take an integral that's a little complex and apply this formula to get a new integral which is easier. So let's see what we have here. We have a 1/2 x e to the 2x minus, okay, well, I had a constant 1/2, and then the antiderivative of e to the 2x is 1/2 e to the 2x. And at this stage, I've evaluated all of the integrals within my integration by parts formula here. So at this stage, I can include the plus c, that is the arbitrary constant of integration. Since this was an indefinite integral, we need to include that constant to find the most general antiderivative. Now in our last step, we'll simplify just a little bit. We've got a 1/2 x e to the 2x minus 1/4 e to the 2x, and then a plus c on the end. Okay. So let's look at another example to see if we can illustrate how this works in some other cases. So in part B, we have the integral of x times cosine of 3x. So again, I see that my integrand is a product of two functions, x and cosine of 3x, and this can't be simplified at all. So since I have a product which can't be simplified, that makes me think, well, let's try this new method of integration by parts. And my first step in this method is to choose part of my integrand to be u, and then the rest of it will be dv. So as with part A, let me maybe choose u to be x, in which case dv has to be everything else within that integral. That is cosine of 3x dx. Now, once I have u and dv, in order to apply the integration by parts formula, I have to calculate du, which would be 1 dx, and v, which would be the integral of cosine 3x, which is 1/3 sine of 3x. So applying my integration by parts formula, the integral of x times cosine of 3x dx, which is what we were calling the integral of u dv, is equal to u times v, which would be 1/3 x times sine of 3x, minus the integral of v du. Now v times du would give us a 1/3 sine of 3x dx. So again, in part B, after we apply this integration by parts formula, the new integral that we're left with is much easier to evaluate than the one that we started with. In fact, it can be evaluated directly from here. So let's see what we have. We had a factor of 1/3 x times sine of 3x. And then we had a constant of negative 1/3. And then the antiderivative of sine of 3x will be negative 1/3 cosine of 3x. And at this stage, once I've evaluated all of my integrals, I can include the constant of integration, plus c. So simplifying a little bit, we have a 1/3 x sine of 3x plus 1/9 cosine of 3x plus c. So this would be the most general antiderivative of that given function. All right. Now, one thing that I want to point out after these first two examples in parts A and B is how I'm making my choice of u. So here we see from our first two examples, when we're choosing u as this function x, when we apply the integration by parts formula, we get something involving du. So we get something involving the derivative of u. So if we make our choice of u as a polynomial, let's say x, when we take the derivative, we just get a constant, 1. Or in general, if I had a polynomial, let's say this was x squared instead of x, when I differentiate x squared, I get 2x, which would be a first degree polynomial instead of the quadratic. So in general, we're going to try to choose u to be something that when I differentiate that expression for u, I get something that's a little easier to work with. And that allows me to get an integral, which might be a little easier to evaluate than the one I started with. So let's look at some other examples. In part C, we have the integral of x squared times sine of 4x dx, which again is a product of two functions, x squared and sine of 4x, and it can't be simplified at all. So that should immediately suggest that we try this new technique of integration by parts. So again, my first step is to choose u and dv. So based off the convention that I was just discussing, I might choose u to be the polynomial part of my integrand. That is the x squared term, in which case dv is everything else. That is sine of 4x dx. So to use the integration by parts formula, I need to find du. So here we would have a 2x times dx, and v would be the integral of sine 4x, which is negative 1/4 cosine of 4x. Okay. So applying the integration by parts formula, the integral of x squared times sine of 4x dx is equal to u times v, which would be negative 1/4 x squared cosine of 4x, minus the integral of v times du. Okay. So let's see what we have here. Taking v times du, let's start by grouping the constants. So we have a negative 1/4 times this 2x, which would give us negative 1/2 x. But here, since I was subtracting this quantity, subtracting that negative 1/2 will become a plus 1/2 of that x times, we had a cosine of 4x and a dx term. So this new integral that I'm left with is the following. And I see here that my integral involves a product of two functions, 1/2 x and cosine of 4x. And this product can't be simplified in any way. So to evaluate this new integral that I'm left with, I'm going to have to apply integration by parts again. So for this new integral, let's make another choice for u and dv. So I'm going to let u be my 1/2 x factor, in which case dv is everything else. That is cosine of 4x dx. So du is then 1/2 dx, and v would be 1/4 sine of 4x. So now, let's see what we have. So this integral that we are after is equal to, well, we had from our previous work, a 1/4 x squared cosine of 4x, and then plus, okay, to evaluate that integral, we have to apply integration by parts a second time. So we're going to take u times v, so 1/2 x times 1/4 sine of 4x gives us 1/8 x times sine of 4x. And then we're subtracting the integral of v times du. So here we have a 1/4 sine of 4x times 1/2 dx. That gives us 1/8 sine of 4x dx. So let's see what we're left with. We had a negative 1/4 x squared cosine of 4x plus 1/8 x sine of 4x. And then we were subtracting 1/8 the integral of sine 4x, which would give us a negative 1/32 cosine of 4x. And at this stage, once I've evaluated all of my integrals, I can include the constant plus c. So this would be the antiderivative of that function. So following our work here, when we were working with this example where our polynomial term in this product was x squared, well, after we differentiated it the first time, we got down to something involving 2x. So after using integration by parts, our new integral that we're left with only involves x times a trig function instead of x squared times a trig function. It got a little bit easier. And when we applied integration by parts a second time, when I differentiated that 1/2 x factor, well, I got down to a constant term. And using integration by parts a second time, the integral that I'm left with is then just a constant times a trig function. We can evaluate that directly. So here we see when our polynomial was involving x squared, we had to use integration by parts twice. So in general, the higher the order of that polynomial, the more times that we will have to apply integration by parts in order to get down to a constant term. So let's look at some other examples. In part D, we have the integral of x cubed times the natural log of x dx, which is an integral of a product of two functions which cannot be simplified. So that should suggest to us that we try integration by parts, and our first step would be to choose u and dv. Now, based on our previous work, we might choose u as the polynomial part of this integrand, x cubed, in which case dv is everything else, natural log of x times dx. So that would mean that du is 3x squared dx, and v would be the antiderivative of log x dx. However, we don't know what the antiderivative of natural log of x is. The derivative of log x is 1 over x, but we don't know what the antiderivative of log x is yet. So if we try to choose u and dv in this way, then we get stuck because we don't know how to integrate that natural log function. So if this ever happens in our work, well, we could just reverse what we call u and dv. So instead of choosing u and dv in this way, let's make a different choice. So let's reverse our choice for each of these. Instead of letting u be x cubed, let's take u to be the natural log of x, in which case dv would be everything else in that integrand, which is our x cubed dx. So then du, well, we know how to differentiate the natural logarithm. We would have 1 over x dx. And to find v, well, if dv was x cubed dx, then v would be the antiderivative of x cubed dx, which is 1/4 x to the 4th. So let's see what we get when we apply our integration by parts formula. The integral of x cubed log x dx, which was u dv, using the integration by parts formula, is equal to u times v, which would be 1/4 x to the 4th times natural log of x, minus the integral of v times du. So let's see what we have. V was 1/4 x to the 4th, multiplying by du, which was 1 over x dx, we're left with 1/4 x cubed dx. So after I apply this integration by parts formula, the new integral that I'm left with is just the integral of a constant times x cubed. And we can evaluate this directly. So here we have 1/4 x to the 4th, natural log x, minus 1/16 x to the 4th. And after we've evaluated all of our integrals, we can include the constant of integration for this indefinite integral. So we've got the following. So in this example, we're illustrating that our initial choice for u and dv might not always work out, in which case we would just go back to the beginning and reverse what we called u and dv. Now in this example, we can see that if our integrand ever involves the natural logarithm of x, we want to choose that as u. We don't want to choose the natural log of x as dv because we don't know how to integrate the natural log of x directly. In fact, to integrate natural log of x, we would have to apply integration by parts. So let's look at another example similar to this. In part E, we have the integral of log x over x squared dx. So as soon as I see that this integral involves the natural logarithm, that suggests to me that I might try integration by parts. As I mentioned at the beginning of this lecture, if our integral ever involves a product, a logarithm, or an inverse trig function, that should suggest to us that we try this method. Now we've seen some examples of integrals involving logarithms, which can be solved using a substitution. You could try a substitution here, but you could see pretty clearly or pretty quickly that it will not work out. So if we stick with this method of integration by parts, let us choose u as the natural log of x, in which case dv would be everything else, 1 over x squared dx. So another way you might think about your integral is as the product of log x with 1 over x squared dx. So I'm choosing u as the log x and then dv as everything else. In which case du is 1 over x dx, and v would be the antiderivative of 1 over x squared, which is negative 1 over x. So applying the integration by parts formula, the integral of log x over x squared dx is equal to u times v, which would be negative natural log of x over x, minus the integral of v times du. So let's look at what we have. For v times du, we would have negative 1 over x squared dx. But remember, we're subtracting the integral of that quantity. So subtracting the negative 1 over x squared, this becomes plus the integral of 1 over x squared dx. And this new integral that we get, we can evaluate directly. So we have a negative log x over x minus 1 over x for the antiderivative of 1 over x squared. And at this stage, we've evaluated all of our integrals, so we can include the constant of integration c. So these last two examples were illustrating that when our integrand involves a natural logarithm, we might try integration by parts where u is taken as that logarithm. So let's look at this next one. I mentioned that we could also use integration by parts to handle antiderivatives of inverse trig functions. So let's look at a problem like that. In part f, we have the integral of sine inverse of x, or if you prefer the notation, arc sine of x. So here, we don't know how to evaluate, or we don't know immediately what the antiderivative of arc sine of x is. So if we don't immediately know the antiderivative, how can we integrate this? And our idea is to make use of integration by parts. So let's see how this will work. We are meant to choose part of our integrand as u, and part of it as dv. So I'm going to choose u as the sine inverse or arc sine of x term. I don't know how to integrate that function, so I don't want to choose it as my dv, because to find v, I would have to integrate it. So instead, let's choose u as this arc sine of x term, in which case dv is everything else, which would just be dx. So to apply our formula, we need to calculate du. So differentiating the arc sine function, well, it might have been a little while since you've dealt with derivatives of inverse trig functions, but reviewing those rules for differentiation, your derivative would be 1 over the square root of x squared minus 1. And then we have a dx. And v is then equal to the integral of 1 dx, which would just be x. So applying our integration by parts formula, the integral of arc sine of x dx would be equal to u times v. So here we have x times arc sine of x minus the integral of v times du. So taking v times du, we have x over the square root of x squared minus 1 dx. So after applying integration by parts, we're left with this new integral. And let's think about how we could evaluate this. So to evaluate this, we could make use of a substitution. When I look at this integral, I see that my denominator involves a composite function, not just the square root of x, but square root of a function of x. And we've said that when we're trying to integrate these composite functions, that typically suggests that we use a substitution. So for our new integral, let's make a substitution. Now typically I would choose u as my variable of substitution, but it gets a little tricky here if you're using substitution with integration by parts, because we've already been using u as part of this integration by parts formula. U is what we were calling arcsine of x. So instead of using u for our variable, let's use something else, maybe w. So when I make my substitution in this integral, I'm going to let w be x squared minus 1, so that dw is 2x dx, and dx is then dw over 2x. So rewriting my integral in terms of w, let's see what we have. So I had the integral of arcsine of x was equal to x times arcsine of x minus the integral of x divided by the square root of what we called w times dx, which we found to be dw over 2x. So simplifying here, I can cancel a factor of x in the numerator and denominator. I'm left with a constant factor of 1 over 2, or 1/2, which I can then bring out in front of that integral. So I have negative 1/2 the integral of 1 over the square root of w dw. Now to integrate that function, I might prefer to rewrite this as w to the negative 1/2 power instead of 1 over root w. So applying my power rule, I have x arcsine of x minus 1/2 of the antiderivative of w to the negative 1/2 would be w to the 1/2, or root w, divided by 1/2, which is equivalent to multiplication by 2. And now I've evaluated all of my integrals, so at this stage I'm going to include my constant of integration, plus c. Now the last thing that I have to do here is get my final answer in terms of the same variable that I started with, x. So as we usually do for substitution problems, well, I don't want to leave my answer in terms of w, so I'm going to substitute w, which was x squared minus 1, back into my answer here. And I have x times arcsine of x, and then here my constants minus 1/2 times 2 leaves me just minus the square root of w, which was x squared minus 1, plus c. All right. So this example illustrating when our integral involves an inverse trig function, we should try integration by parts where we choose u to be that inverse trig function, because we know how to differentiate those, but finding the antiderivatives of these inverse trig functions requires integration by parts. So let's look at one last problem for this lecture. We're looking at the definite integral from 0 to 1 of arctangent x dx. So again, if you prefer the notation, you can say this is arctangent of x dx instead of tangent inverse, just a matter of notational preference there. So as soon as I see that this integral involves an inverse trig function, I think to myself, well, I should probably use integration by parts. And my first step in the method of integration by parts is to choose u and dv. And as we saw in our previous example, we should probably take u to be the inverse trig function. That is arctangent of x, in which case dv is just dx. So to use this method, we need to calculate du. So the derivative of arctangent x is 1 over x squared plus 1 times our differential dx. And if dv is equal to dx, then v would be 1x. So applying our integration by parts formula, well, let me start by looking at the indefinite integral of this arctangent x function. So for now, I'm going to ignore the fact that this is a definite integral. Let me just calculate the antiderivative first, and then at the end, to evaluate the definite integral, I'm just going to take the values 0 and 1 and substitute them into what I find for my antiderivative here. So using integration by parts, we would have u times v, so x times arctangent x, minus the integral of v du, which would be x over x squared plus 1 dx. So this new integral that I'm left with can be evaluated using a substitution. I see that my integrand involves a quotient of two polynomials, which can't be simplified. And I mentioned in our chapter 1, or our section 1.5 material, that when we're looking at integrating a quotient of polynomials, we might try a substitution first. So to evaluate that new integral, let's make a substitution where our new variable, w, will be the denominator, x squared plus 1, so that dw is 2x dx, and dx is then dw over 2x. So rewriting our integral in terms of w, let's see what we have. The integral of arctangent x dx is equal to x times arctangent of x minus the integral of x over w times dx, which was dw over 2x. So we can cancel a factor of x in the numerator and denominator, and that leaves us with a constant factor of 1/2, which we can bring out in front, and we're left with the integral of 1 over w dw. So we have x times arctangent of x minus 1/2 the natural log of absolute value w. And here, once I've evaluated my integrals, I can include the constant of integration, plus c. So substituting w back in, we have x times arctangent of x minus 1/2 of the natural log of w, which was x squared plus 1, plus c. Now you might ask, what happened to the absolute value here? Well, I'm taking the absolute value of w, but w was x squared plus 1, which is always positive. Remember, x squared is always at least 0, so if I take that and add 1, I get something which is always at least 1. So I don't need the absolute value there. This value for w is always positive, so I can drop the absolute value. Now we're not quite done. What I found was the indefinite integral of my arctangent x function, but recall this problem was a definite integral of that arctangent function from 0 to 1. So once I find my antiderivative here, I can evaluate this definite integral, using the fundamental theorem of calculus by taking this antiderivative and substituting in 0 and 1. And here I can omit the constant of integration there. Since we're looking at a definite integral, it doesn't matter which antiderivative I use, so we could take c to be 0. So let's see what we're left with. When I substitute 1 in for x, I have arctangent of 1 minus half of the natural log of 2. And then we subtract what we get when we evaluate at 0. So I have 0 times arctangent of 0 is 0, minus half of the natural log of 1. Now recall the natural log of 1 is 0. So I'm just left with the first two terms, the arctangent of 1, which is pi over 4, minus half of the natural log of 2. Okay. So this last example, again illustrating an example where we would be working with an inverse trig function. So we want to use integration by parts where u is chosen as that inverse trig function. And this also illustrates how to handle a definite integral in the case that we're using integration by parts. We could first go through the work of finding the antiderivative of our function, and then at the very end I can use the fundamental theorem of calculus to evaluate my definite integral by plugging in my endpoints to the antiderivative that we